So let's begin. Sometimes we need to talk about motion in 2 or even 3 dimensions. I know this can seem confusing, but the good news is you know how to do all this stuff. We've been dealing with one-dimensional kinematics, and you're pretty good with all that for right now. All we really have to do is divide motion into x, y, and possibly z directions. You can extend this even into more dimensions if you want to, but we really seem to live in a 3-dimensional universe, so it's not necessary. Just as a sidelight here, if we were studying general or special relativity, we would extend this into another dimension, that of space-time, using both the speed of light and time to figure things out. We're really not going to do that, so don't worry about it. We're going to treat each dimension separately, and then we'll use the trig we know to combine the results into 2 or 3-dimensional vectors. We'll also assume that the acceleration in each direction happens to be constant. This is primarily what we do in physics. Once in a great while, we'll have to vary or deal with varying accelerations, but for right now, we don't have to deal with that. Just remember, your acceleration can be positive, speeding up, negative, slowing down, or even 0, but it's going to be a constant value. So here's what we have. We have equations in the x direction. The acceleration is constant. V final x equals V initial x plus axt. X final equals x initial plus V initial xt plus 1/2 axt squared. These are familiar equations. Not surprisingly, the y equations are going to be identical, just substituting the y subscript for the x subscript. And if we needed to have something in z, we would have an identical set of equations for that as well. Now substituting the z subscript for either the x or y subscript. To find the absolute value or the magnitude, you just use the Pythagorean theorem. So the absolute value of the acceleration is ax squared plus ay squared plus az squared, the square root of that. Same thing for velocity, same thing for displacement. Just as a note, we generally call displacement from the origin r, so r is equal to the square root of x squared plus y squared plus z squared. Remember from your math class that those two vertical lines mean magnitude. Technically, it's absolute value, but it still means magnitude. It's the hypotenuse of the right triangle formed in either 3D or 2D. So this is a little bit different from projectile motion. If we're talking about projectile motion, we know some things about what's happening. We know that the acceleration in the x direction is going to be 0, and we know that the acceleration in the y direction is minus g. But in general, 2-dimensional or 3-dimensional motion, the accelerations are either given or we'll be able to calculate them using our kinematic equations. Any of the kinematic equations we've used before will still work for 1D or 2D. It's confusing, and I know that. So make sure you know the difference between a generalized 2-dimensional or 3-dimensional problem and that of projectile motion. I'll be very, very clear when we're dealing with projectile motion, and that's almost what we'll almost always deal with. So just be aware of the differences. So let's try an example problem. Here's a particle in 2 dimensions. It's going to start at x equals 1, y equals 3. That's going to be our initial values, with an initial velocity of 4 meters per second in the x direction and minus 2 meters per second in the y direction. And then it's going to have an acceleration of minus 0.5 meters per second squared in the x and 1.5 meters per second squared in the y. I want to find the position, the velocity, and the acceleration at time equals 7 seconds. Acceleration's easy. Can do that very easily. We defined it earlier that it's going to be a constant, so a at 7 is going to be minus 0.5 comma 1.5 meters per second squared. But remember, we always have to express vectors in 2 different ways. So using some trig, we're going to find that the magnitude of the acceleration is going to be 1.6 meters per second squared, and the angle is going to be 72 degrees above the negative x-axis. Notice when I did the inverse trig, I did not put the negative 0.5 in there. You have to draw the vector yourself to see where it's going. And remember that there's always 2 ways to express a vector, either in the xy form or in the r at theta form. I want you to be able to do both. Now we need to find the velocity. We can use our standard kinematic equations, and we can find that the velocity in the x direction at 7 seconds is equal to 4 plus minus 0.5 times 7, that's going to equal 0.50 meters per second. In the y direction, I'm going to get v of y at 7 seconds is equal to minus 2.0 plus 1.5 times 7, that's going to equal 8.5 meters per second. Putting those together trigonometrically, I find that my velocity is going to be 8.51 meters per second squared. I know I'm using 3 sig figs rather than 2. I just picked bad numbers for the demo because otherwise my velocity would be about the same thing in the y direction. My angle turns out to be 87 degrees above the x-axis. Again, if I write that as a vector, v at 7 seconds is equal to 0.5, 8.5 meters per second. Now let's find the position at 7 seconds. Again, I'm going to use our standard kinematic equations. I'm going to find that the x at 7 seconds is about 16.8 meters. Put in all the numbers, I should get 16.8. I do the same thing for the y. I find that to be about 25.8 meters. Make sure you can do this math. Again, the math isn't hard. There's just a lot of it to do, and many places you can mess up. To find the magnitude of my displacement, I just use the Pythagorean theorem. I find that I'm about 30.8 meters away from the origin at 7 seconds. And that gives me an angle of about 57 degrees above the positive x-axis. In xy form, r of 7.0 seconds is 16.8, 25.8 meters. Bottom line, it's nothing more than motion in multiple independent directions, and you know how to do this. Just remember that you have to do some trig to find the final a, the v, and the r. The graphs will look like they did for one-dimensional. R versus t is a parabola. V versus t is linear, and a versus t is a constant value. There are some minor complications with this due to the vector nature of r and v, especially if I have negative values in the x or y directions to start. Nothing to really worry about. So here's a graph of r versus t for the example I did. Notice I ran this for a long time, up to 500 seconds, but my graph looks very parabolic, just like we expect it to be. Here's my v versus t. Again, I ran it for 500 seconds. It looks like I have a constantly increasing velocity. It's in a linear way. So everything's fine. You know how to do this. Just some practice and you'll be okay.